Alright, welcome. This is the lecture that will take place on Tuesday, March 17th. So, where we ended on Thursday, that's the end of Exam 2, so now we're starting stuff that will be on Exam 3. So we'll finish Chapter 6, we'll move into Chapter 7, Chapter 8, and then we'll see how far we get. So, that's the plan for Exam 3. As far as this stuff goes, hopefully this is okay. These videos, the format and all of that. If you have any comments or suggestions, let me know. Send me an email. Yeah, I don't know. We're still figuring this out. So let's continue. So we ended on page 7 of the Chapter 2 notes. So now we're on page 8. Chapter 6 notes, I think is what I said. So now comes the fun stuff. Now comes sometimes the shortcut. So if you go back and you look through most of the examples we've done, they all have some similar characteristics. For the most part, our examples, certainly recently, we've had independent trials. So we've done some selections with replacement. That's generally independent. And many of the other examples, we were able to assume independence between trials. And for the most part, the events that we were interested in had two outcomes. There was something we wanted, say like selecting a consonant, and there's something we didn't want, and that would be selecting a vowel. So in general, there's kind of a pattern to those types of problems. And mathematicians back in the 1600s figured out what those patterns were, and they realized there were shortcuts, and it made their lives a little bit easier, especially with gambling stuff. So, when you have an experiment in which your trials have exactly two outcomes, those sometimes you'll see them called a Bernoulli experiment. So there's a success and there's a failure, and that's it. Now there can be more than one outcome. It's just you assign multiple things to being a success, multiple things to being a failure. So for example, maybe the simplest case is flipping a coin. There's heads, there's tails. Now, success in general, this is what you want. And a failure in general is what you don't want, meaning you don't want to see it. Now, success doesn't have to be a good thing, failure doesn't have to be a bad thing. So there's a field in statistics called survival analysis, and I'm no expert, but I've dealt with it a little bit. Generally, a success is when something dies. You've observed the end of an observation. It's not a good thing. So success doesn't have to be a good outcome. It's just whatever you're interested in measuring. So flipping a coin, heads or tails, two outcomes, independent trials. Rolling a die, you can get a 6 or not a 6. So maybe the 6 is your success, not a 6, which includes 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. Those would be the failures. So a failure is just a set of things you don't want, and a success is something you do want. So if we have a Bernoulli experiment, so we've done something, there are two outcomes. If we do a lot of those Bernoulli experiments, maybe we do it n times, so n is going to be the number of trials, and those trials are independent of one another, meaning probabilities don't change, the outcome of one trial has no effect on the outcome of any other trial, then if we set up our event of interest, the thing we call x, our random variable, if we want that to be the number of successes that we've observed in the n trials, so we're counting successes, that setup means our random variable follows a special probability distribution called the binomial distribution. If you've taken some calculus classes, you may have encountered this when you talked about series. We won't get into that level of detail. And we'll see several more of these specially named distributions. They arise because they apply to certain situations, and they have nice mathematical formulas, which we will use via the calculator. We won't actually write out any formulas. But they have nice mathematical formulas which kind of make it easier to work with in terms of finding probabilities. So here's an example to sort of introduce the idea of the binomial. So here we're going to be rolling a fair die. It doesn't say that, but we can assume that 5 times, or maybe we're rolling 5 die, it doesn't matter. And we're interested in the number of 5s we see. So big X, our random variable, is the number of 5s in 5 rolls. And maybe we're interested in setting up the probability distribution for this random variable. So the first thing to think about would be, well, what are the values of little x? How many 5s could we see? So we could have none, all the way up to all 5 could be 5s. Okay. So what we would do is we could go through and we could find the probabilities of all of these. And we've done examples like this at the beginning of the notes. So the continents problem, the left-handed people example, same idea. This one is just a little more complex because there are 6 outcomes of interest. So it's just a lot more work. So let's first focus on this. What's the probability that we see exactly 3 5s? So what this is saying is we want to know what's the probability that big X, the number of 5s we have, is equal to 3. Okay? Well, we would have to start thinking about how can we see those 3 5s in the 5 rolls. So here are some examples. Maybe you get 5, 5, 5, and then something that's not a 5, something that's not a 5. So all of your 5s come first, and then you have 2 not 5s. And then we can think about, okay, here's one outcome. We can find its probability. So we're essentially saying, what's the probability that we get a 5 on the first roll, and a 5 on the second, and a 5 on the third, and not a 5 on the fourth roll, and lastly, and not a 5 on the last roll. We know that dice rolls are independent. It's kind of like coin flips. So we just can multiply those probabilities straight together, special multiplication rule. So the probability of rolling a 5, well, that's 1 out of 6. So we have 3 of those being multiplied. Rolling something that's not a 5, well, there's 5 out of 6 chances to do that. So we have 2 of those. And we can rewrite this. So 1/6 times 1/6 times 1/6 is the same as 1/6 to the third power. 5/6 times 5/6 is the same as 5/6 to the second power, or squared. So we've seen this setup before. When we get to values in the middle of the probability distribution, we have to first find the probability of one of the outcomes, and then if we know how many different ways we can observe that specific value of the random variable, then we can just multiply that one probability by however many ways, however many combinations there are to see that particular outcome. But this one would require a little bit of work. So you can go through and think through all of the different combinations, but like we've seen in other examples, no matter what order the 5s and the not 5s appear, the probability calculation ends up the same. So what we have to figure out is, well, how many different ways can we have exactly 3 5s? And for right now, I will just tell you that the answer is 10. And we'll come back to see how we could compute that if we wanted to. So then what we have to do to find the probability that x is 3, that's still the goal, we're going to take the probability of seeing one of the outcomes, so 1/6 to the third times 5/6 squared, and then we have to multiply this by, well, how many different ways did we see this? So we multiply that by 10. Okay, and we'll leave it like that just for now, because this setup sort of feeds into what the binomial distribution is all about. So let's look at just a couple more probabilities from this probability distribution, and maybe we'll start to see a pattern. Okay, so we'll write out the probability distribution. So we could have 0, we could have 1, 2, 3, 4, or 5 5s. And we just found the probability for 3 in kind of a quick way. So we saw that this was 10 times 1/6 to the third times 5/6 squared. Okay. So let's go to the easy ones. So let's go to the beginning and the end of the probability distribution. So let's imagine we want to find the probability that x is 0. So translating that, what's the probability that the number of 5s in our 5 rolls is 0? So what's the probability we roll 0 5s? What that means is we roll all not 5s. So we know that we're going to have the first one being not 5 is 5 out of 6, and the second one still 5 out of 6, and so on for all 5 rolls. Okay, and we'll rewrite that as 5/6 to the 5th. For now. We will rewrite it one more way in just a moment. We'll jump down to what if x is 5? So in this case, all 5 rolls are 5s. So the chance that the first one is a 5 is 1/6. Chance that the second one is a 5, also 1/6, etc. for all 5 rolls. And we can rewrite that as 1/6 to the 5th. Okay. And let's do one more. Say, let's do x equals 1. So what's the probability that one of the rolls will be a 5? Okay. So one option, if we think about our 5 rolls, 1, 2, 3, 4, 5. So maybe the 5 comes first, and then we have 4 not 5s. Okay, that's one option. And then we can start to think about the rest, and we've sort of seen this before. So essentially the one that we care about is the 5. So it could be in the first slot, it could be in the second slot, the third, the fourth, or the last slot. So what that means is there are 5 different ways to have 1 5 in your rolls. It could be first, second, third, fourth, or last. So if we find this probability, we have 1/6, and then we have 5/6, 5/6, 5/6, 5/6. So I'll just write that as 5/6 to the 4th. Okay. So when we fill this into the probability distribution, we will have something that looks like 5 times 1/6 times 1/6 to the 4th. Oops, sorry, that should be a 5/6. Okay. Now, let's step back to when x was 0 and x was 1. What we want to do is we want to try to make it look like the probability that x is 1 and the probability that x is 3, because these are pretty similar. The beginning number is just an integer, but it changes, that's okay. Then we have 1/6 with some power. It's not explicitly written there, but there's a power of 1 here, and a 5/6 to some power. So let's rewrite these one more time. We only have one way of seeing 0 5s, and we can put the 1/6 in here, but we'll put it to the 0th power. Anything to the power of 0 is equal to 1. So basically right now we have 1 times 1 is 1 times the 5/6 to the 5th. And we'll do the same thing for x equals 5. We can put a 1, because there's only one way to see 5 5s, times 1/6 to the 5th, and then we'll bring in that 5/6, and again we'll give that one a power of 0. That means it's just 1. So 1 times 1 is 1, times 1/6 to the 5th is 1/6 to the 5th. So we're not changing the probabilities, we're just putting all of the pieces in there to make it look like x equals 1 and x equals 3. Okay. So if you start to look at these 4 probabilities that we've written down, we still don't know 2, we still don't know 4, but that's okay. You can start to see a pattern. Maybe the first thing you would notice is that the exponent of 1/6 is always little x. So here 1/6 is to the 0 for the probability that x is 0. And here the power was 1 when we wanted the probability that x is 1. The power is 3 when we wanted x equals 3, and so on. And what you may also notice is that if you add up the exponents, 0 plus 5 is 5, 1 plus 4 is